I'm James Johnson, and you're watching Niagara Pro Tips. Welcome back to this multi-part series on BQL. Hopefully you've had a chance to take a look at the previous videos, which cover the basics of the BQL syntax using the help, the base sort and extent, projection, and predicate. In this video, we're going to focus on the order by clause and aggregate and scalar functions. So the order by clause is used to sort data. And you'll see this in the syntax that occurs after the having clause. So it's going to be at the end of the BQL statement. And this is used to sort the results. And you can specify either ascending or descending. The default sort order is ascending. So honestly, you don't need to specify that, but you can. And the results can be ordered one of three ways. You can use a path expression like out.value, a column alias that's specified in your projection, or the column position and using a one base index. And there's some cases where counting is done with zero base index, which is pretty typical for software. But in this case, it is a one base index. So you can see in the example at the bottom where we have a BQL query that's looking for control numeric points in the station. And we've got a projection that's displaying the grandparent of the control point, which is the device, its display name under a column aliased as floor. And then we're showing the name of the device under a column aliased as zone, and then the value of the control point using the value with facets method as a column aliased as room temp. And in the green text there, you can see order by one, meaning first I want to order by the floor alphabetically, and then I want to order secondly by the out.value, meaning the space temperature values or room temp values. And we want to do that in the highest to coldest, so descending order. And then lastly, saying to sort by the alias zone, which is the column that has the device names in it. So each one is processed in order, and so you'll get subsorts based on the items that have matching values. So let's take a look at that real quickly. And this is something that's not supported in the BQL query builder, but it is certainly something that you can add with your syntaxes in a bound table or in a raw query or a BQL grid or things of that nature. And so we'll just open up this save bookmark query. And you can see in this case, what we're doing is just looking at the BACnet network. And so we're doing a BQL query, and it's scoped to the BACnet network. And we're searching for the control points under the BACnet network. And then the projection, in this case, is getting the proxy extension from the point, then getting the device and the parent of that, which happens to be a device folder, which are the floors. And we're displaying that as floor as the alias. And then we're, again, using the proxy extension .get device call to get the name of that device or display name, whichever one we wanted, the name as a point. I guess in this case, I actually have a predicate which is filtering just down to the space temperature points. So probably could have done things a little bit differently with numeric point here instead. But in the event, we have some results here. So if we want to order these results, then what we can do is go to the end of this query and we'll add in order by. Let's put some spaces here so you can hopefully see a little bit better. And then we can put the index number, the alias, or a path expression. So if I put order by one, and the default behavior is ascending sort order. So if I want to be descending, then I would type in the keyword DESC for descending. And you can see now that the results are sorted by the floor column in a descending sort order. Now, if we wanted to subsort by another column, we put a comma, and then it could be another index number, or it could be the alias of the column, or it could be a value. So, for example, if I wanted to put the air handler zone names in descending sort order, then we could use the alias zone instead of the index number being 2, and then I can specify descending as well. So currently the zones are being sorted ascending alphabetically. And if I tell it to force it to sort descending, now we get reverse alphabetical order under each of the floors that are also being sorted by reverse alphabetical order as well. You can certainly also sort by the path statement, so like out.value, which in this case is not actually in the projection. I'm using value with facets in the projection, but I can sort by a path statement that doesn't have to be part of the projection. Again, if I don't specify the descending sort order, then it's going to be ascending, lowest to highest value. And so you can explicitly put ASC for ascending sort order, but if it's assumed if I don't specify descending. So now if I specify descending, we'll see that it provides us a highest to lowest value of the space temperatures then. The same sort of thing applies to histories as well. So in, I suppose, alarm database, you could order by any of the results there as well. So for example, if we were looking at air handler 1 room temperature for last week, and we have our historical data that we've queried, normally it's going to automatically sort by timestamp from oldest to newest. And if you really wanted to change that, we could do an order by and say timestamp descending order. And in that case, we're looking at the most current record here, and it's going backwards in time then, but it defaults to ascending sort order on the timestamp column if you don't otherwise specify. We can certainly also pick the value column and either sort in ascending by default or descending order. This would show me the highest room temperature in the previous week in descending order of the values. So again, order by just allows us to sort in order the results that might bring the information we're looking for to the top of the queue. All right. So let's take a look at some scalar and aggregate functions. And with scalar functions, they're designed to operate on a single value from a single row, but it allows us to do some data manipulation or to insert some parameters where typically BQL doesn't allow us to run methods that require parameters, and this is an exception to that rule. The scalar functions that exist in the core BQL, there's a slot exists, which takes a parameter, which is a string. That's going to be the name of the slot that we want to search for. And also a property exists method that also takes a single quoted string as well. All properties are slots, but all slots are not properties. So we also have topic and action slots as well. So the slot exists would allow me to test for an action slot or a topic or a property that was named something, where property exists is only going to test the property slots and not the actions and topics. There's also a substring function, and this can be helpful maybe in cases where you have a gateway device where all the points maybe have a name like air handler, HU_1 underscore, and then some point name maybe, and you're trying to do a substring function or something of that nature. It's certainly possible that the substring function might come in handy for you. So take a quick look at a couple of those things there. And it is possible to use scalar functions in the query builder, but in this case, I'm just going to open up some saved queries here. And in this case, we'll see the slot exists function. And all I'm doing is passing in the BACnet network as a base ord, and then using the BQL query with an extent that's looking for numeric points, and then using the scalar function in the predicate. So testing for numeric points that have a child property slot or any kind of slot. Property could be action or topic in this case, it's numeric interval. And the results you'll notice in this case are for the numeric points which have history extensions underneath them. So looking at my BACnet network, at my air handler points, we're finding things like the room CO2, room humidity, and room temp and supply temp all have slots named numeric interval. And again, the other option that we have there is property exists, and that's going to narrow it down to the properties that have that name. So it's essentially exactly the same. It's a scalar function here, but using property exists instead of slot exists as the function that we want to call. And then scalar functions, we also have substring. And you can see in this case, I'm not saying this is this is more of an academic example here than a real world example, I'd say, but we're looking at the BACnet network for numeric points, and then the projection is displaying the name of the point in the first column, and then I'm using the substring function as the second column, and the substring takes 3 arguments. It takes a string, which is the string that we want to feed into process, and then the start and end index of the string that we want to include with that substring function. So you can see in this case, I'm telling it to start with character 0, the first character, and include 5 characters. And so you can see the results there in the other column. Just a standard substring function. There's some other scalar functions, and these already made mention of in the previous video with the predicates, and I'll just give a little bit more explanation on these. These are scalar functions, which allow us to pass in an argument, and the lower function will convert the given string to all lowercase characters, and the upper function will convert the given string to all uppercase characters. Most likely these would be useful in your predicates with comparing names of things without case sensitivity being a concern. But take a look at this real quickly and close some of these extra tabs that are accumulating. And we'll look at these aggregate function, or scalar functions rather, lower. So you can see in this case, again, base ordered against the BACnet network, and looking for numeric points. And then the first column is just displaying the name of the point, and the second column is calling the lower scalar function and passing the name in. And you can see it's just converting any uppercase characters to lowercase in the output. And the opposite of that would be the upper function. And if we look at the upper function, it's going to be identical other than the function name being upper versus lower. And you can see the results are, in this case, it takes all the lowercase letters and converts those to uppercase. Right. A couple more scalar functions that we have here. There's 2 scalar functions for checking whether a tag exists on a component and also for getting the tag value. Both of these functions take 2 strings. So in single quotes, the first string will be the namespace of the dictionary, and the second string will be the name of the tag. And the has tag would normally be used within the predicate to help identify components within the station that have a specific tag associated with them. The get tag would be used in the projection, and it would display the actual tag value. So not as handy for, say, a marker tag, but definitely some kind of a value tag like a string tag or an ord or BQL time or something of that nature. If you are going to use the get tag function in your projection, I would suggest that you use the has tag function in the predicate for the same tag to verify the tag exists before trying to call the function in the projection. I will also say that NeQL is really the best way to query for tags and relations and that sort of thing. However, there might be cases where using BQL for this is also useful, particularly maybe if working with commissioning agents and trying to document how a system is definitively tagged. And you could certainly use BQL and export the results to show what specific tags and what their values might be that are on each of the components in the station. So, taking a quick look at this, I have a couple of examples here that are saved. Scalar functions, my has tag. Pretty straightforward. You can see has a base ordered like normal, and the extent in this case is from control points. And then I'm looking for points where they have the tag and colon history. So these are the only 3 components in this case under my BACnet network which have a history extension that's actually enabled in collecting. Hence, they have the history tag on them. And if I take a look at the other example, this will actually display the history tag, which is the history ID, is the value of the history tag. So we can see for each of these histories, checking both with the predicate, has tag, history tag, and then in the projection, I'm using the get tag function, scalar function, to display the value of the history tag in that case. So there's also an option for you to create custom scalar functions, and this is covered in the doc developer. You can create your own module and create your own scalar functions, which can definitely be useful. There's a number of scalar functions that exist in the Vicom Pro module. If you have access to those modules, you can check out the help topic on the lib class, and it has information about using those scalar functions. In addition to scalar functions, BQL also supports aggregate functions, and aggregate functions operate on a set of values and they return a single summarizing value. Might be all of the values in the set, or it could be some conglomeration of certain sets of values within the entire data set. The standard aggregate expression functions that we support are count, max, min, average, and sum. Count has a little bit of a special syntax to it in that it allows using an asterisk character for the function parameter. Or it could be the name of the slot, like you could say count and then parentheses out or status, which would count the number of out slots or status slots from each of the components. But the asterisk is typically the easiest thing to utilize with that count function. The rest of those functions, the max, min, average, and sum, I'll take a control point or be status numeric value, like an out slot property for the function. Take a look at this, and you can use these in the query builder as well. I do have some examples that are saved here. So taking a look at this, we'll see syntax is pretty basic in this case. We're just scoping the query to the BACnet network, looking for control points, and then in my select, in my projection, I'm using the count aggregate function and using the special asterisk character. What this does is then it resolves the base sort and the extent and finds all the control points under the BACnet network. It applies this function to that whole set of objects, and it returns a single answer, which in this case happens to be the number of control points which have been found. If I change the query a little bit here, and in this case, we're looking under the BACnet network for numeric points, or control points rather, that are named room temp. Once it finds that set of objects by resolving the base sort and the extent and the predicate, then it's going to apply the functions in the projection. So this aggregate function of max says, go get the out slot, which is a status numeric, from each of those control points, and it runs that aggregate function on it, and it returns the result, which is the highest value or maximum value out of the set. And close some of these extra tabs and talk a little bit more about functions. Very similar to the scalar functions, it's also possible for you to use custom aggregate functions as well, and it's covered in the developer documentation as well. Along the same lines of these aggregate functions, there is a history rollup function which aggregates history records, numeric history records, into less granular results. So it could take 96 records from a day and return a single summarizing value for the daily intervals. This is obviously only valid for numeric type histories then, and the results of the history rollup function have a schema that includes 2B abs time values. There's a timestamp column, which is the first timestamp in that rollup interval, an end timestamp, which is the last timestamp in the rollup interval, the count, which is the number of items in that interval, and then the min, max, average, and sum are all the aggregate functions being applied to that set of history records. The history rollup function has two syntaxes that are supported. The first one, you'll notice that instead of it saying select after BQL colon, it will say history colon, which is the module. History rollup is the Java class, and then dot rollup is the function that's being called. And the function requires one of two things. The first option there is a relative amount of time, so a Baja rel time. And in this case, we're using the syntax for a B simple, where it's the Baja is the module, colon, rel time is the class, and in single quotes are the number of milliseconds. So that's the number of milliseconds in 1 day. We also have support for a rollup function using an enum. And you'll notice in the second example, this is a case where I mentioned in one of the earlier videos about the extents that there's certainly a case where we might want to use the history ID as part of the base ord instead of using the from extent keyword. We can limit the period of the data being returned. We talked about this in the video on the predicate portion, so we can limit the history records to say last week. Then the BQL query is still using the same history rollup, and rollup function, but instead of a relative amount of time, we're going to give it certain rollup interval period using enum tags. And the main reason for this is because of daylight savings, for example, where you might have 23, 24, 25 hours in a day, or variable lengths of number of days in a month, right? 28, 29, 30, 31 days, or variable number of days in a year. So using these periods will better handle those variable time periods in that case. So let's take a look at what these examples look like. And we'll go to these aggregate functions that I have saved. So we'll see this rollup in this case is hourly rollup. I think I said daily a moment ago, but it's hourly values that are being rolled up. So we can see that we're querying the air handler run room temperature for a period of yesterday, applying the history rollup function, and we're giving it a Baja rel time with that number of milliseconds, which are the number of milliseconds in 1 hour. So you can see in the table that we're getting 24 results. And the schema includes the timestamp with the beginning record of the interval, the ending timestamp of the interval, how many records are in that record set in that row, and then what is the minimum, max, average, and sum of all those four values in this case in each of those sets. So the aggregate function's operating on a set of values, and it's returning a single value for that set of values. And we'll go take a look at this other example also. Very similar, but we're going to be using the enum tags there instead of the rel time value. Same, or in this case, looking at the main KW history and a period of last week, and we're applying the history rollup function. And then in parameters in the parentheses, history colon rollup interval is our enum type, and then the single quotes are the tags that we want to look for. So we want a daily rollup or hourly or monthly and so forth are our options. Right. I'm going to talk also about the group by and having clause, and talk about how those are supported. The group by clause is not explicitly supported by BQL, but if you use an aggregate function in your projection and you have some unique path in the projection as well, the BQL engine will implicitly define distinct groups there. And you can see in this example, although I only need one aggregate function, I have multiple aggregate functions in the projection. but I have a unique path expression like name. So that allows it to find the control points that all have the same name, and it applies the aggregate functions to those then using that grouping. Taking a look at what this might look like. Can't quite get it all on one screen, but we're looking at the BACnet network. And we're looking for numeric points that are named room temp or room humidity. And my projection has the name of the point, and then also the min, max, sum, average, and count functions, all passing the out slot into those functions. So you can see that in this case, when the query runs, it finds a count of 30 points named room humidity and 30 points named room temp. And because there was a unique path expression of name, it implicitly created the groupings, and then it applied those aggregate functions to those groups of points. And this is providing my high value, my low value, min and max, as well as the average and the sum. In this case, I only have 2 devices communicating on the BACnet network, so it found 30 points, but out of those 30, only 2 of the points had OK statuses and values, which are then used in the functions in this case. There's also an option of using a having clause, and the having clause is sort of like the predicate. It has to be a Boolean expression, and that expression has to be based on an aggregate function. So the way the BQL engine works is it will resolve the base ord and the extent, and also the predicate to process and get that result set. And then the having clause then can aggregate information to decide what to exclude from the results further. You have to specify a projection, so it can't be a blank projection or a wildcard projection or the all projection. You have to specify columns. You can see the having syntax in purple, the keyword having, and then some aggregate function that we want to test for. So in this case, we can see that the sum of the room temperature points is 157. We could then use the having clause to filter out our results that are being displayed here. So in that case, it would be having and then some aggregate function. In this case, we'll say the sum of the out slot is greater than 150. And now I only see the room temp results, even though the predicate and the extent are finding and processing room humidity and room temp. I've excluded the room humidity results from the result based on that having clause. So the predicate itself cannot exclude things based on aggregate functions. That has to be done with the having clause. So hopefully you found this information useful for the order by on your BQL results, as well as the aggregate and scalar functions and the having and group by functionality as well. Stay tuned for another video in this series where we'll go through some of the keywords and miscellaneous parts to the BQL functionality as well. Thanks for watching.